Hi, everyone. Welcome. We have like another minute before we get started, but I wanted to do a couple quick announcements. Thank you all so much for being here. This is actually going to be a really exciting session. I've seen Rick talk several times, and it's always very entertaining, and people go on and on about how amazing he is, and I'm like, what about me? Anyway, but after this, so this is going to be about 30 minutes, and then after this, there's going to be lunch. So I just want to give you heads up that lunch is going to be served in the food trucks that are outside in front of the venue. So we'll have some food truck food for lunch. And then don't forget to sign up for Ask the Experts in the Expo Hall. That's where you get your private consultations with Ask with MongoDB local experts. You could also request Rick. I volunteer him. And all of these sessions will be recorded if you're getting a lot out of it, but you just can't absorb as quickly as we speak. Don't worry, it's going to be recorded, and you'll be able to see them on YouTube later. And I'm going to let Rick's intro is so long, I'm going to let Scott take over from here. Oh, sorry. I guess you need this.
Microphones might help. I'm loud, but not quite that loud. All right, guys, so I actually just met Rick, but reading his bio and hearing about him from Karen, this guy's really kind of got it going on. So he leads our developer relations team at Mongo for our strategic accounts, our pod accounts. And prior to joining Mongo, he was the worldwide technical leader for NoSQL services at AWS. He was responsible for migrating thousands of workloads from RDBMS to NoSQL. He's established a center of excellence for NoSQL design at Amazon during that migration and defined the best practices and design patterns used today by thousands of Amazon internal service teams. Rick currently operates the technical leader for the global strategic account team, where he's responsible for building the market for MongoDB technology by facilitating the creation of similar center of excellence capabilities within our customer organizations. He brings over 30 years of technical expertise to the Mongo team. He's got over 9 patents in cloud virtualization, complex event processing, root cause analysis, and NoSQL database technologies. So with that, I will turn it over to Rick.
Great. Thank you. Thank you, Scott. Thank you, everybody, for taking the time out of your day to come see us here at MongoDB Local and hear me talk a little bit about a topic I'm very passionate about. I have a long history in NoSQL technology. Obviously, I ran some a service team, an SA team at Amazon Retail. It was called the Black Belt Team for NoSQL Technology, which was involved in assisting that organization in one of the largest, if not the largest, technology migration in the world. As we migrated over 3,000 Oracle Server instances and over 10,000 application services and workloads to NoSQL technology. One of the things that we're here to talk to today is why. Why did Amazon make those decisions? I mean, an organization doesn't just decide to throw out a database, right? I mean, especially a database, the relational database, Oracle, was a key component of, the foundation of the infrastructure of Amazon. Why do you make a decision to re-educate 25,000 developers in a new technology that they don't understand? And how do you do that, right? And that comes down to understanding a little bit about the reasons why we've made those decisions in the past. So we'll talk a little bit about that. What were some of the reasons and some of the decision-making factors that people have made over time when we make these decisions? Because the relational database wasn't what we always had, right? So let's take a look in the past, because the past tells us what we need to do in the future. If you don't pay attention to it, you're going to repeat it. And then it's about making it work, right? One of the things that we found at Amazon, which was interesting, was that developers are really, really good at following a path, but they need to actually be shown a little bit of the way first. And what does that really mean? How do you retrain a development organization that is so embedded in a technology, right? Rooted in a technology like the relational database. And how do we do that? And how do you manage a technology transformation like that at enterprise scale? What does it mean to make these types of things happen? And these lessons learned are interesting because they apply to any organization trying to make a technology transformation or a technology shift, not just a large enterprise. But the first thing we want to look at is why. Right? Why did Amazon make this decision? Amazon, a lot of people think, was an organization that was born in the cloud. But the reality is Amazon Retail was founded in 1995. That was a decade before the cloud even appeared. And even when the cloud first arrived in 2005, 2006, when EC2 was first launched, it was certainly not a technology that was suitable for running many, many, many enterprise workloads, right? Actually, it's very few. When we were a $5 billion company before Jeff actually wrote that letter. You may be familiar with the letter about service-oriented architecture. We said all future development at Amazon will be SOA and microservices. That was, we'd been operating for a decade. We were a $5 billion company. We had thousands of services built on monolithic stacks, and those services didn't go away, right? They didn't just go away overnight. As a matter of fact, by 2018, the scale was breaking many, many things inside of Amazon, including a lot of those monoliths, right? They were running on complex database architectures that were scaling beyond what the systems were capable of delivering. We had the largest Oracle license in the world, right? We had the biggest Oracle RAC deployments in the world, and we were stretching and breaking everything. And it wasn't really that, honestly, that drove the change. What drove the change was the cost. And this is really what the mission was of what we called Rolling Stone. Rolling Stone was the project we launched internally to deprecate 3,000 Oracle Server instances. And that was the mission of that project. It wasn't to replace the relational database technology. That kind of happened along the way when we started looking at what are we going to do this. The initial plan was to take those 10,000 application services and really just kind of carve off their databases and lift and shift all these workloads into RDS instances running on Postgres Aurora or Postgres, Postgres Aurora or MySQL Aurora. But the reality was that replacing the relational database wasn't something anyone was really thinking about, right, when this project started. There were things that happened we'll talk about in a little bit, but that came along the way that kind of drove us down that path. But it was really the cost of the relational database of the Oracle license, right, that was driving this change. Okay, so you got to understand that. No enterprise makes a decision to replace a technology on a whim. And again, the decision wasn't really to replace the relational database. It was to replace Oracle with a more effective version, so to speak, of that relational database. But some interesting things started happening along the way when we started actually breaking things down. And it's important to understand what happens in database processing and why you actually want to make these changes to understand what happened when we started making this investigation. When you look at the history of data processing, right, it's about a series of what I call peaks and valleys in data pressure. Okay, data pressure is the ability of the system to process what you're asking it to process at a reasonable cost or at a reasonable time. And when one of those dimensions is broken, that's a technology trigger. And we're going to start inventing things. We've invented many, many things over the years, right? The first database was the one we were born with. It's a great database. It's between our ears, right? When my eyes are open, it's online. It's highly available. But it's a single-user system, right? Questionable durability, zero fault tolerance. We're not going to build enterprise services on that. So we started doing something to store structured data, which is the definition of a database. We started writing things down, okay? Ledger accounting ran public and private sector services for many, many millennia until the 1880 US Census came along, and a man named Herman Hollerith was tasked with collating all of that data. And it took him 8 years of that 10-year cycle to do that. And he realized that in 1890, when he had to execute a similar task, he was going to have to do something different because they weren't going to be able to get the job done. Again, it was taking too long. It was too expensive and too slow. So he invented the machine-readable punch card and the punch card sorting machine, and the era of modern data processing was born along with a small little company called IBM. I spent about half a decade at IBM myself. Interesting relationship that company has with the database sector, technology sector. As a matter of fact, they kind of drove it and fueled it for many years, almost 100 years. Many innovations came after that: paper tape, magnetic tape, distributed block storage, hierarchical management systems, and eventually, around 1975, 1980, a guy named Edgar Codd came along and invented the relational database. What's interesting to know about this is that Edgar Codd was on a mission, and his mission was clearly stated in the abstract of his paper, right, which stated that future users of database systems will need to be able to ask questions of their data without having to write code. That was his mission. And the normalized data model and System R and all of the development that occurred around that was really built to deliver that mission, but he did not believe he would ever be able to do it, and neither did anyone else at the time, because the time complexity of the relational queries were too expensive compared to the hierarchical management systems of the time. So everyone thought this is a nice idea, Ted, but it's a theoretical exercise. Well, a little thing happened, right? That was, the friend of the relational database. It was called Moore's Law. And the time complexity of the relational query kind of became insignificant as the processor speed increased, right? But this trend broke. And this is what we found at Amazon, and this is what changed the whole game when we were looking at Rolling Stone, right? And now we fast forward to 2022, and we're looking at a new technology, NoSQL databases, because they're distributed and they're high efficiency, and we're going to break this down in a second. But one of the things we need to understand, and this is probably the biggest driver behind the NoSQL database today. You can talk to me about data models, you can talk to me about developer efficiency, and these are all good reasons to choose a NoSQL database, don't get me wrong, but the fundamental reason the enterprise needs to be looking at this technology is that it's cheaper, majorly cheaper. If you look at what's happening today, right, Moore's Law is no longer the enabler for the relational database. All the fears, all the critics, they turned out to be correct just 40 years later. In 2014, if you look at the chart there on the left, that's the top 500 supercomputing clusters in the world today. In 2014, it fell off a cliff. They have not even been able to hit Moore's Law predictions year to year for almost a decade now. Right, this is what we saw at Amazon in 2017, 2018, when we were going through the Rolling Stone project. Per core performance, single thread performance was flattening out in the server processing space. Where are you seeing that kind of Moore's Law increases? And this is the reason why Moore's Law is not a law. It's a financial equation, okay? It's how much money are we going to spend to double the transistor density every 2 years? And in the server processing space, not enough, okay? In the mobile device space, we're seeing that because 5 nanometer CPUs, those are a loss leader. When I have a device that's going to lock you in for 3 or 4 years on a subscription service, I'm going to make up the cost of that CPU. But you're not going to make up that cost in the server processing space. So we're not seeing that kind of efficiency gain anymore. What does that mean? That just means that the relational database is not getting any cheaper. It's getting more expensive every single day. So this is one of the things we saw. A couple other things that drove this, but the biggest thing here to understand is the CPU performance is flattening, but the cost of storage continues to fall. We pay pennies for gigabytes, for terabytes today. We used to spend thousands of dollars for this storage, right? So the efficiency gain in storage, it actually drove significant return for the relational database by deduplicating that data on disk is no longer there. The storage is dirt cheap. The CPU is again, the most expensive resource in the data center and something that we need to concern ourselves with. This is not new thinking, okay? This is not me talking to you. This is Edgar Cod himself who called this out in his seminal paper, right? Relational model for data for large shared data banks. The normalized data model is efficient for storage purposes. It's efficient for bulk communication of data between systems, but denormalized data models will decrease the CPU load for common queries. That's a key learning. Right? High velocity queries are where you spend your money. Low velocity queries are where you don't have to worry about those things so much. You just need to accommodate them. Right? So when we start modeling data, if I can actually shift the data model to drive efficiency in my high velocity queries, I'm going to be doing myself a favor. That's key learning right there from the man himself. The other thing he talks about is over-normalization. You see this all the time. Little tiny lookup tables joining in on every query. You know, back in the day, they used to tell you don't do that because the CPU ticks that you're spending on joining every one of those rows when you have like an event table that gives like event states, info, critical, warning, and I'm joining that in on every single lookup. I'm just adding time complexity to the query. That used to matter a lot, right? It's starting to matter a lot again. So don't over-normalize your data. Again, even Edgar Cod himself talked about these things 40 or 50 years ago. This is not new thinking. So when should I be looking at NoSQL and when should I look at traditional relational database? Well, the answer there is actually the days of the relational database are done. This used to be where we were, probably 3 or 4 years ago before platforms like MongoDB introduced SQL read APIs, but the reality was the OLAP workload, that was the domain of the relational database. Why? Because relational database supports ad hoc queries. Those ad hoc queries, you don't know what those questions are going to be. Someone comes in at the end of the day, they write some report, who knows, maybe if it's a report, I know what the query will be, but again, an analyst, somebody running an analytics workload, those are interesting workloads because they're not latency sensitive, right? I just need to get the answer. Doesn't matter if it comes back in 10 milliseconds or 100 milliseconds or 2 or 3 seconds, right? As long as I get the answer. And they don't run at high velocity. I don't run a report 1,000 times a second, right? I run a report once a day, once a week, once a month. So as long as I can handle those access patterns, it doesn't really matter how efficiently, that's okay, but what really matters is those OLTP workloads, those things that 90% of the applications we write code for are OLTP, right? They're process-driven, they're transactional, they run the same queries every time the process executes. They don't run a different query every single time that you make a request, right? When the user clicks the button, the same thing happens every time. These are well-understood access patterns, and these are the ones that run at high velocity, thousands of times a second, billions of times a day in the Amazon framework of things, right? Maybe not so much at scale in other organizations, but this is the area we want to focus on when we start talking about driving efficiency. And this is why NoSQL databases really shine. We'll get into this in a second, but the reality is if I can tweak the data model to support the access pattern and drive efficiency there, then those high velocity patterns become cheap. And as long as I can support those low velocity patterns, we're in good shape. And this is why NoSQL databases today, like MongoDB, offer those SQL read APIs, because we can now handle those OLAP workloads that all that BI tooling is tied to, right? The SQL is the language of data. Everybody understands it. We have MQL, it'll deliver similar results, but you have to learn it. You have all this tooling already to hook up. Well, you can do that now with MongoDB. And again, think about it. The OLAP workloads don't run at high velocity, and they don't require low latency. So I can tell you right now that will that SQL query execute as efficiently, as neatly as it does on a relational database? Probably not. But do you care? No. Because again, as long as I get the answer at the end of the week, I'm okay. As long as Monday morning on the board meeting, I have the data I need, we're in good shape. Right? The quarterlies only have to run once every 3 months. Right? Who cares if they come back in 100 milliseconds or two or 3 seconds? That's irrelevant. What matters are those, again, those high velocity queries, right? So a couple lessons to kind of think about there, right? You want to think about the nature of the access pattern, the time complexity of those queries. But the key thing here is making it work, right? And access patterns are what drive cost, okay? When we were looking at things at Amazon, what we found was that 70% of the access patterns across all of our services were hitting a single row of data on a single table, right? 20% more were hitting a range of rows on one table. And it kind of makes sense when you think about it, because OLTP workloads are typically write heavy. They don't really read often as much as they write. And those writes and those updates, they're all going to what? To tables, to single rows on those tables. They have to be. A range of rows is an update maybe. And a lot of the read patterns, they're just getting a single row of data off that table or a range of rows of data off of a single table too. So when you combine all this together, most of the access patterns are pretty simple, okay? 90% of them, single table. But 10% of the access patterns drove 50% of the infrastructure cost. And that's because of the time complexity of the joins, right? When we break things down, it's all about relationships, okay? The applications don't use data in big, large chunks. Applications use data in little bits and pieces. That's what that was telling us. 70% of the access patterns for a single row on a single table. That means 70% of the time I don't need a big, large relational blob of data. I just need that one little row that's that sub-element from that relational structure. And that's important because if you don't design your data model right, and we'll talk about this in a second, you're going to drive a lot of inefficiency when you're using NoSQL. But you do need to understand how to model those relationships efficiently, or it's not going to work. Right? I like to say there's no such thing as non-relational data. There isn't. Can you describe it? I don't know what the definition is, right? Non-relational data, that's the stuff I don't care about. That's the data on the hard drive before I format it, right? It's the static in the air between the stations on the radio, okay? It's something that doesn't matter. That's non-relational. If I'm working with data, it's relational, and I need to understand the relationships. I need to be able to model those relationships efficiently, or the database doesn't work. And we found this out really quick when we were working at Amazon. Okay, this is the pattern, and this is where we break down the actual time complexity and get into why the relational database is done, okay? When you look at this relational model of a product catalog on the left-hand side, this is Amazon's, simple version of Amazon's product catalog. We've got one-to-one relationship between books, one-to-many between albums and, tracks, many between videos and actors, right? And one-to-one between all the products, okay? If I want to go get a, list of all my products, it's 3 different queries, 3 different levels of complexity, and so, but I can't really do that very easily. And if you think about the access patterns against this data structure, they're all product-centric, right? Get me product by ID, get me the products in this category, get me the products the cheaper than X or whatnot, whatever your filter conditions are, but I always want the product. So maybe what I want to do is don't store this data relationally, and I probably wouldn't even do this in the relational database. I would put a cache in front of this, a product, result cache or something, so I would select out of the cache, right, to offload the relational database. I think we've had multiple presenters talk about how that injects more complexity in the stack, but it's pretty obvious if I have to worry about cache synchronization in front of my database, that's a problem. That's complexity. Maybe I should just store the data in the data structure that is actually requested by the application and required by the application. In this particular use case, works pretty good to create these product objects. I might not model all data this way, But in this case, since I really have product-centric access patterns, the data is relatively immutable. It updates every now and then, but the updates cost isn't really going to be high here. It's a read-heavy service, okay? So this is a really good data structure for that. Now let's break down what happens when we look at the actual time complexity of those joins and why it works better to do it the other way. When you look at this particular access pattern, we want to go and get the book, right? The time complexity for that one-to-one join, that's not terrible. But these are all CPU ticks, and when we start adding tables, it just gets worse, right? The one-to-many join, the many-to-many join, and these are not complex queries, right? Some of the SQL I saw in some of the earlier presentations is more representative of the stuff we see in production for complex services. It's very complicated. Those time complexity calculations are enormous, right? Joining the data is expensive, very expensive. When you look at model joins in NoSQL, and we're actually going to explain how to use not just a key value access pattern, but a relational pattern here, right? Because again, 70% of our access patterns are a single row of data, not 20% for a range of rows. That means I'm accessing data in little bits and pieces, not big, large chunks. So maybe for some applications, that's not a good idea to put these big blobs of data together. So let's talk about what that looks like when we actually need to express relationships, right? So I'm going to create some product objects here that describe the product's base information. In this particular case, we have these data blobs. Data is the metadata that describes a product. I only put a couple attributes in there. There could be many more. That's kind of the property bucket that is what I'm selecting, right? I don't really care much about that. But what I do care about is what is this thing related to? Because let's say I have different access patterns. It's not just a product catalog. I want to, track relationships between these entities. Maybe the authors and the books they wrote, the publishers, the musicians that performed, the songs, whatnot. So what we're actually going to do is tack an array of relationships onto all these objects. That's in the targets array there, and this is going to come into play in a second. But if you're looking at the key value access pattern, it's always just an index lookup, right? It's O log n. So as I select these items by ID, I'm just getting the metadata that describes the product, the array of pointers that describes what they're related to. Doesn't necessarily describe the extended data of what's related to yet. We'll get there in a second. But any one of these lookups is O log n because it's just a key value lookup on the document. That's great. Ooh. Let's go ahead and throw in some more dimensions here because, like I said, we want to track relationships between the entities. So let's put in the actors, let's put in the directors, let's put in the songs, let's put in the, all of the various pieces, the authors of the books and everything. And again, let's decorate all these objects with the relationships that they have to each other now, right? Essentially references, right? And now let's go ahead and index those target arrays and see what happens. So if you think about what a relational database does, at its core, its job is to join tables together and join indexes on those tables, okay? If I take all those objects and I put them into one collection, like in a NoSQL database, an interesting thing happens when I draw an index across the shared attributes. Essentially, they're joined already. The indexes are already merged. There's no need to join those things anymore because I can select the grouping with a low time complexity just by querying the indexed attributes. So in this case, get me all the books that an author wrote. Get me all the people that somebody's related to, right? Get me all the albums where a song appeared. Give me the studios that recorded it, the musicians that performed it, so on and so forth. Get me all of the movies that actors been in. Actors might be producers, publishers, and directors as well. So I could have any relationship that this person might have to any other object that I put in this collection. Essentially what I've done here is I built an adjacency list. It's a many-to-many relationship. You could look at it this way. Those target arrays are the mapping rows from your mapping table, more or less. and essentially, this data structure is not denormalized. This data structure is actually normalized because I'm not duplicating the data. I might be denormalizing some pointers here and there. Some people might get into nitpicking there, but I'm not deduplicating the data. And Edgar Cott himself talks about that normalization has nothing to do with how the data is stored. Okay, it's how the data is actually represented logically. So I'm not violating any of those tenets of normalization by doing this. But what I am doing, if you look at that time complexity down below, right, it's O log n, O log n, O log n. The many-to-many join, the most complex query I had in my list. What's the time complexity here to produce the exact same result? It's O log n, okay? So you can't argue with the math. It's going to be much more efficient to query a NoSQL database and NoSQL data structure than it is to query a relational database using this similar data structure, right? If I go with homogeneous tables, it's just going to be less efficient. Okay, so one of the key things we had to learn at Amazon when we actually went to go execute the plan was the fact that this is kind of not really common knowledge, right? People don't understand how to model data this way. A lot of people learn that third normal form. That's what you learn in school. They still don't teach this properly in college today, in computer science curriculums today. I'm actually working with several professors trying to get them to introduce the correct curriculum because they're just way off. Many people are way off in how to use NoSQL today, right? The reality is, again, you got to think about the size of the data I'm working with. The application uses data in bits and pieces. That means I need to structure that data according to the way the application uses it, or I'm reading and writing data that I don't need to read and write. Okay, so this chart really tells us what happens in an organization when if they don't understand how to use the technology yet. Right? In the beginning, we have a technology trigger. This is data pressure. It's too slow. It's too it's not fast enough. It's not cheap enough. We're going to invent something new. We've invented this new NoSQL technology. Some people might argue that we're revisiting the hierarchical management systems of the past, but the reality is NoSQL databases today are a lot different than that. Regardless, few people know how to use them. That's the reality today. We're still in that early adopter phase, right? Not a lot of people really know how to use NoSQL databases. It's not the mainstream technology in most enterprises yet. I believe it will be for all the reasons we just talked about. So what happens is people start running these solutions, they hear about them, and they go in with these inflated expectations, and they have a miserable experience, right? And this is actually what happened to us at Amazon, and probably the best example of this is the shopping cart service, right? So I talked to the shopping cart service team because they came back and said, we can't use NoSQL because it's too expensive compared to the relational database. What do you mean it's too expensive? And we actually went to go look at what they're doing. Now, the shopping cart's an interesting thing in Amazon. It's a mainline service, what we call a tier 1 service. And basically every customer is using it. And the way customers use the shopping cart is they typically don't add all the items all at once, right? You add items one at a time, okay? Again, working with data in bits and pieces. In DynamoDB, the minimum unit cost is 1 kilobyte. It's uncompressed data. It's pretty merciless when it comes to cost. And this is what was happening, is they would build a shopping cart, they had an array of items for the cart, and then the items started getting worked with by the system in various ways. What fulfillment center are you coming from, right? And just being added, and deleted from the cart, right? The customer would add one item, it was 1 kilobyte, 1 WCU. They would add 2 items, now it's 2 kilobytes. They would add the third item, now it's 3 kilobytes, because you're reading and writing the entire document every time you're adding an item to the cart, okay? So the solution to this was to actually go ahead and say, look, we're just going to create an item per item in the cart. On the DynamoDB table, there's a partition. It's a shopping cart ID. We'll have one item in that partition. It's going to be the shopping cart metadata. We're going to have every other item in there will be an order item. Now we can work with those order items individually of each other. We can add one, delete one. It's always 1 kilobyte, 1 WCU. As we update the information of a given item, where it's being shipped from, whatnot, again, 1 WCU. So we reduce their cost by something like 80 to 90%, right? Because most shopping carts, if you think about it, people add items, they go check out, they delete items. You might have 12 items in the cart for a week, and you're adding items and removing items. It's amazing how people use that thing like a database, right? Just the shopping cart. And this was driving enormous cost. So optimizing the data model is key to driving the efficiency in any NoSQL database, right? Once people understand how to use the technology and the ecosystem kind of gains that skill set, then we have better results. Now, one of the things we found at Amazon, which was really interesting, I had a really neat experience at Amazon. When I first went to the SA team, I worked with customers. Then I went and worked with the Amazon retail team. And I had an organization behind me called the Plus team. So I ran the Black Belt team, we had the Plus team. Plus team was marketing and sales. Black Belt team was technical delivery. What I found there is when you align the marketing and sales behind the technical delivery, that's when you get results, okay? And this is what we saw. We delivered a program there we call, there was DynamoDB Day, but I'm bringing the technology and the process to MongoDB, right? MongoDB now, we run these tailor engagements to accelerate projects within our strategic accounts. We found it at Amazon that teaching the developer through workshops and hackathons was interesting, and it got some results, but not really great results. We got the best results when we showed the developers how to solve the problem they're working on with the technology that we're trying to use. And that's what we do. We sit down, we'll give you the brown bags and technology deep dives and breakouts, but instead of workshops and hackathons, my team puts data modeling experts on site. We sit down with your developers one-on-one and work through your problems, your solutions, and understand, here's how our technology works for you. We'll give you a prototype of a data model, and developers are pretty smart about taking that and running with it, right? I mean, there's plenty of documentation out there to solve all the problems you need to know about APIs and SDKs and all this stuff, but there's not a lot of information out is how do I solve the problem that I'm trying to solve with this technology, right? So what we found was that once we had these whiteboard sessions, right, with subject matter experts, it's like a kickstart to those teams. It gets them going down the road. And it's a learning exercise for both of us, right? The team and my team. I found out everything I know about NoSQL design today comes from the teams I worked with. They know their data better than me. They'll come back to me in a week or two and ask me, is this the right thing to do? And I'll look at what they'll do and I go, that's brilliant. Now I'll use it somewhere else. So oftentimes I reuse a lot of what I learned from my customers when I go to the future customers that I'm working with. So if there's anything you can take of the conversation we had today, please understand, NoSQL is not about non-relational data. NoSQL isn't even NoSQL anymore, right? It's no RDBMS. That's really what it's about. And the reason why, because that's legacy tech. It's slow, it's expensive. If you're not looking at NoSQL as a strategy going forward as your primary platform, you're making a mistake because your competitors are. And I'm working with them, so I know. Again, relational database is done. Its efficiency is declining. It's never coming back. Moore's law is off the charts when it comes to server processor. And the NoSQL API is not just for OLTP anymore, right? And MongoDB, as we heard earlier today, it's not just a database anymore, right? We heard a lot about how developers want more than a database. They want search. They want online archive. They want federated queries. We gave you that. It's all integrated. It's not just a bunch of disparate technologies you got to stitch together with baling wire and duct tape. It's an integrated solution. All right, so that's what I've got for you today. Thanks so much. Hit the QR code. Tell them you like me. If you didn't like me, then there's another code somewhere you can scan. All right, thanks, guys. Appreciate it.
Give another round of applause for Rick, please. Couple of announcements before we take the break here. So first off, we are recording every session. They're going to be available after the event. So if you're trying to decide between two, we are going to have a recording available afterwards. The food trucks for lunch will be outside, so head to that venue. And if you're wanting to get an Ask the Expert session, I believe that's on the upper floor up there. So please go ahead and go up there and sign up so we can get you scheduled with some of our experts while we got here. With that, we'll head out to lunch.